It's just about density, I feel.
Episode 3. So,
So, you're taking my line. Okay, so the point of this conversation is that we want to give the audience some core understanding or fundamental understanding of physics. Why? Because in the wellness world, when we're talking about energy, like especially if you're like looking at wellness content online, there's so much stuff about energy, but it's super shallow. There's no depth to it. And it's shallow because even though it's based in these like ancient traditional wisdom systems like yogic or Chinese medicine or plant medicine, because it's so far removed in our society, people are just taking like these high level concepts and there's no depth to what they're saying. It's very shallow. They're not giving you really like a good rationale or at least like a good understanding of what they're talking about. It's just kind of like woo woo, whatever. So when we think about energy in the wellness context, that's what we think of. But when we think about energy in the natural sciences, in physics, for example, we're talking about electricity, which is fundamental to not just the world around us, but our physical makeup, the world internally. Our body runs on electricity. So I think the point is to merge the two and see how, okay, we're actually talking about the same things, but can we take the rigorous science and integrate it with these ancient wisdom practices to give people, our modern day society, more depth into why these practices might help them on an energetic level. And we can really see, I think, the overlap between the two worlds, and then people can get a better understanding, essentially.
okay.
Yeah. Let's start with biophysics.
So think of biophysics as, let's say, an interdisciplinary science, which involves various natural sciences, mostly physics. And it applies theories from physics or methods from physics to study biological systems,
Okay.
such as the human being or the human body. And then under biophysics, you can think of a whole range of topics and concepts that biophysicists typically study.
So before we move on, so biophysics or biomechanical physics, is that?
So biophysics is more general because
Okay.
biomechanics typically focuses on the mechanical
Okay, so we're
aspects.
still in the biophysics.
Exactly.
Mechanical is like one level
So
down. Okay. Sorry.
an example of biomechanics is movement.
Okay.
How do you convert chemical energy in your body into mechanical energy to move?
Okay.
You can call it biomechanics. More generally, biophysics is a slightly more general field.
Okay.
You take essentially various theories and methods from physics applied to the human body, including mechanics. So
Okay.
mechanics would be one of them.
Okay.
Another example would be optics. So how do you actually sense the world? That's also
Like your vision.
your vision. You can also look at, let's say, electricity, as you said. So the nervous system, essentially, you can think of as a network, electricity network, which is run by ions. And
Which are?
so ions, shall we slightly try to...
Yeah. Let's break down these
terms.
concepts. So ions.
okay,
Let's start with ions.
Let's talk about all the important ingredients in the body.
Okay.
Ions is
Perfect.
one of them.
Yeah.
So ions are charged molecules.
Okay. All molecules have to have a charge?
So molecules usually are neutral.
Okay.
But
so no charge?
No charge.
Okay.
So the number of protons, which are positively charged, let's say entities, if you want to call them, are equal to the number of electrons, which are negatively charged.
Okay, it's taking me back to
Taking you back to high school.
Chemistry and physics, yeah.
Exactly. Protons are positively charged particles. Electrons are negatively charged particles.
Okay.
Both of those compose atoms and molecules. And usually these are neutral, so their numbers are equal.
Okay.
But then you have cases where they become charged. So your molecule or your atom loses electrons or gains electrons. So if it loses electrons, it becomes a positively charged ion.
Okay.
So examples in the body.
Because it's taking away the negative.
Exactly.
Okay.
So examples in your body include sodium, let's say.
Okay.
So when you eat table salt, that's actually neutral. But then in your body, sodium becomes charged. Sodium is actually very important in your nervous system.
Yeah, sodium and potassium. It's the interchange of these ions that allows electricity to manifest
Exactly.
essentially. Yeah.
Chloride as well, for example.
Yeah.
So all of these ions are very important in your nervous system because they essentially dictate how electricity flows.
So they're like the little
Charges.
that when they move around and they go from being like positive to negative, that movement creates like an effect on a level up, which translates to electricity. Could you say that?
That's a simple way of explaining
Okay,
it. Yeah. So
perfect.
that's essentially electricity.
Okay.
And that's electricity in the brain or in the nervous system more generally. And
Mm-hmm.
this is essentially how your body functions
Okay.
through the flow of electricity in it.
And is that charge transfer?
So charge transfer, we can talk about it a bit more generally. Charge transfer is the process by which an atom or a molecule either loses or gains charge.
Okay.
And this process is very important in your body and on a lot of these reactions that happen in your body involve charge transfer. So charge transfer is another important, let's say, concept
Okay.
in the body, which is in a simple way of thinking about it is gaining or losing charge or electrons.
Okay, so it's what you described before.
Exactly.
And we need that because of it facilitates all the downstream
biological
movement.
processes.
Okay,
Yeah.
cool. Then what about biomechanics?
So biomechanics, you can think of. So there's this field in physics called mechanics. What mechanics is how, let's say, put it simply, motion. How motion happens, whether humans or cars or fluids. And this thing is very important in the body because a lot of what we do is movement. Whether we're walking, whether we're running, when we breathe, breathing is a movement. Your diaphragm essentially moves. So all of this can be thought of as a biomechanical system. How do biological processes affect and get affected by some form of movement?
Okay.
So that is what biomechanics tends to study.
Okay. And it's important, like I'm now thinking about like the implication to our health. It's important because obviously like the way, like if you're thinking of your body as a machine, like the integrity of that machine, the integrity of its processes, how well it does what it's supposed to do is directly related to your health and your quality of life. And if at the most fundamental level, there's an energetic component to it, it's important to understand like what the chain of events, like the downstream chain of events is to get like the full picture.
Exactly. And we can give a quick example on this, rating it to energy. So think of your body as a biomechanical system. Think of it as an engine or a machine, as you said. It needs fuel. This fuel is a form of energy. When this fuel comes into your body, it changes the fuel to something it can use to move.
Okay.
In other terms, you're eating food, you're getting nutrients, you're breathing oxygen. This chemical energy in your body is transformed into mechanical energy for you to move. Say you're, let's say, malnourished. You're not eating well, you're not breathing well. Your chemical energy is going to get affected, which will affect your mechanics. So you won't be able to move, you won't be able to run, you will be low on energy, per se, in normal terms.
And I think like that's a really good example. And even to take it one step further to like a real life problem we have in our society is like people not knowing how to breathe properly. Like we're in a constant state of shallow breathing. Like most people only breathe into the upper part of their lungs. They're not breathing deep into their diaphragm. And that shallow, strenuous breath has an implication on your energy resources, doesn't it?
Yeah, definitely. And same thing with food.
Like I remember you were saying last time that like the more strained your breath is, the more you're actually losing energy, right?
So exactly, you can train your, let's say, biology, or you can train your body to actually be efficient on its usage of oxygen using certain techniques of breathwork. The way you breathe, as you said, is very different across humans, and this difference actually causes differences in how your body uses it and if it's efficient in using oxygen or not. So the more you're trained in breathwork, the more efficient your body actually is in allocating oxygen.
And that's because you're not losing heat, right? Isn't there the heat
So your
element?
body becomes more trained to, let's say, reduce the amount of dissipation. Dissipation is heat, basically.
Okay.
Yeah.
So the less heat you use, the more energy you preserve.
Yes.
Okay.
Think of it this way: the more good energy.
And that comes from like the ease of your breath,
Exactly.
the ease and depth of your breath.
Yeah.
Okay, we'll get more
We'll get
into
more
that in another episode.
and the less strain your diaphragm is. As you go
Exactly.
ahead.
Actually, like I had a yoga teacher once say to think of receiving the breath rather than forcing the breath. And I feel like that little cue really helped me like relax when I was breathing, and I could feel that like it really optimized. Yeah. Okay, awesome. Any other fundamental things you think we need to cover?
I think the last thing, probably because it might come up in some of the future episodes, is something very popular with people, which is quantum mechanics.
Okay, yeah, quantum. Let's get into quantum.
Quantum mechanics is very important to the human body.
Okay.
It's also a very sort of popular topic, which a lot of the yogic science tries to relate to.
And a lot of the woo science want to talk about quantum and whatever. So this is, yeah, we need to like get clear on what quantum is.
Quantum mechanics is the study of physics, let's say, at the microscopic level.
Microscopic.
Microscopic,
Okay.
so the quantum level. You study electrons, protons, what we talked about, atoms, molecules. But then the perspective is slightly different there, because you get, I can explain it quickly, this thing called wave-particle duality.
Wave-particle duality.
Yes. So to simplify it, think firstly not at a quantum level, but a classical macroscopic level.
Which, okay, let's use that more. So just like a surface level.
Surface level, okay. The normal world, the macroscopic world. You think of things as being fixed out there you can study. So Hannah's there, I can study Hannah moving. The quantum level is slightly more complex, because particles are not actually particles in that sense. They're more, they're better thought of as waves.
Okay.
What waves are disturbances, or let's say movements of energy across space and time. So this is where it becomes more complex.
So we're moving from, let's say, like if we want to like have a mental framework, we're moving from thinking about ourselves in the material physical world to the flip side of that, which is ourselves in space time.
Not ourselves necessarily, to be specific.
Yeah.
But
existence.
The approach of studying physics, or the approach of studying systems, moves from fixed pinpointed particles and things into movement of energy in space and time, which is what waves are.
So rather than focusing on the material, we're focusing on the space, the realm of space, the space in between.
Yeah, the movement of, let's say, whatever we're going to call them, particles or entities, in a more wave-like format.
Okay.
Wave-like form, I mean.
Okay. And then like we can, I guess an example is like sound permeates, it waves through
space. Exactly. That's an example. Another example is electrons do not become these pinpointed particles moving, they become a flow of energy.
Flow?
Flow
of energy. Okay.
So they become a wave, fundamentally.
So that, I mean, just as someone, like as an outsider, I know that like the distinction of what makes something quantum is that like particles or everything exists in wave form until it's observed. That's when it collapses into particle form, right?
So think of quantum mechanics as, at what level does the wave nature of things become important?
Become important?
At the macroscopic level, I don't need to think of Hannah as a wave.
No, because you wouldn't get anything
exactly
done. Yeah.
But then at what point, if I zoom in, does this wave nature that we talk about become fundamental in understanding things? That is what that's the quantum level.
Okay.
So it's when the wave nature of things become
relevant.
Exactly.
Okay.
Exactly.
And the threshold of when particles become waves.
That's a very good question, and it's a whole space of study in physics: quantum emergence. Coherence, decoherence. Yeah. So I think these are just general concepts. I think each one of those will have its sort of in-depth episode on its own, especially the applications of quantum mechanics in the human body.
But for just to like kind of wrap it up high level, when we're talking about quantum, we're really talking about energy moving in
small
space.
Scale, exactly.
Very small scale.
Yeah.
And then
space
I
and
think
time.
For me, space and time, but even just to add like a last thought on it, and wrap it back to subjective experience, I think that's where we get into the realm of mind and mindset and intention
That's we can
and
try to draw
attention.
parallels as well with
Yeah.
non-traditional.
Because how do we direct this energy? If I want to do something, if I want to type on my laptop, I first have
You're directing energy.
I have to create the intention, which
Yes.
creates the impulse, which then creates the
And
action.
all of that is energy flow.
And all its energy flow.
Yeah.
Super cool.
Looking forward for the future ones.